Welcome to the After On podcast. I'm your host, Rob Reed, and this is a series of conversations with thinkers, founders, and scientists. Take a little time and stretch out, because these talks are unhurried and meant to bring you to a top percentile understanding of something important. So, whether you're into startups or ideas, a techie or a lit major, take your time, engage your mind, and you'll be glad you did it. Especially this week, when we'll be talking to
Yale astrophysicist Priya Natarajan, one of the world's leading experts in black holes and dark matter. Priya and I hadn't yet met when I first reached out to discuss the possibility of her appearing on this show. But before we recorded our interview, we crossed paths this summer at Tim O'Reilly's weekend-long sci-fu gathering at the headquarters of Google X. Not only that, but Priya and I were assigned to the same small sci-fu subgroup. Now there's an alliteration, which operated a bit like a homeroom class back in middle school. Meanwhile, Priya was spending the summer in Cambridge, Massachusetts, and I passed through there a couple of times. One time to attend a board meeting, another time to interview David Reich, also to research a piece I'm writing for the New York Times. And in the midst of all that, Priya and I ended up at a couple of the same dinner parties. We caught up a couple times to discuss this interview, and so by the time we sat down to actually record it, we were pretty good buddies. The result was what I've come to think of as the Stuart Brand effect. As you may remember, Stuart was my guest back in June, and because he and I go way back, we ended up talking for hours. Well, so did Priya and I. So today I'm doing the same thing I did with my Stuart episode, which is I'm posting a shorter version of the interview to the main podcast feed, and I'm making the full extended version, the director's cut, if you will, available to backers of this show who have access to my Patreon feed. That's those who support this show with donations of $5 a month or more. The interview itself, excluding the intro and outro, is almost exactly 50% longer in that version. So if you are a backer, you may want to listen to the rest of this introduction because the Patreon version does not include the intro. Then hop over to the Patreon feed when the interview starts and hear the whole thing. The extended version includes quite a bit more about black holes, dark matter, and dark energy, the mysterious corners of the universe, which collectively comprise the vast majority of the universe. Ordinary matter, the stuff that comprises you, me, Earth, the sun, every planet and star, even every black hole, accounts for just 4% of the cosmic inventory, which is a fancy way of saying all the stuff in the universe. 26% of the cosmic inventory is dark matter, about which we know just a smidgen. And Priya knows that smidgen extremely well because she actually discovered some of it herself. The remaining 70%, 70, of the cosmic inventory is dark energy. What little science does know, Priya lays out in the interview, which doesn't take very long. In both versions of the interview, we also get deep into the subject of black holes. Priya is one of the world's top experts on this subject, and she may have made a really significant discovery about black holes. That's pending confirmation by the James Webb Telescope, which will hopefully launch into orbit in March of 2021. Priya and I discuss her potential discovery in both versions of the interview, a bit more in the longer one. The longer version also includes a lot more of her fascinating globe-spanning background, what drew her to astronomy as a kid growing up in India, also her philosophy of scientific history, which she studied quite extensively, etc. Really, there's just a lot more about everything in the longer version. Now, if you're listening to the shorter version, I do want to stress that second syllable. It is shorter, but it is not short at all on an absolute level. The interview alone is well over an hour. And by the very nature of it being shorter, it's quite tightly edited. So I promise you will learn a ton. By the way, the reason I'm creating two versions, as with the Stuart Brand episode, is I want to be respectful of your time as listeners, but I also didn't want to fully discard any of the fun tangents or deep dives that our conversation included. And since my patrons are in the habit of diving a bit deeper into my work via the bonus content I post in my private feed, they'll hopefully see the extra time as being a feature rather than a bug. And incidentally, if you're not backing the show at a level of $5 a month or more and feel like you're missing out, I, of course, invite you to join the party over on Patreon. Just head on over to patreon.com/Rob Reed. Reed is spelled R-E-I-D. And with that, let's get into this fascinating conversation about the universe's vast unknowns with Priya Natarajan. First, Priya, it is great to be here in your beautifully air-conditioned living room here in the Boston area, where I've had a delightfully packed few days. And I was initially marveling at how convenient it is that you're in Boston for part of the summer. But then we realized a couple of days ago that I was literally across the street from your place in New Haven when I was interviewing Rick Fromm. Talk about a small world.
I know, totally. And Rick's mom lives in the same building.
Oh, does she?
Yeah.
Well, it's a small world, even when bridging the disparate domains of ornithology and astrophysics. Anyway, your recent book, which I recommend to any listener with an interest in the cosmos, is called Mapping the Heavens. And it's not just a somewhat poetic title, but maps have meant quite a bit to you throughout your life, haven't they?
For me, maps encode knowledge, and they encode the state of knowledge at a given time. And so in the pre-scientific era, you can look at maps and look at the progression in conceptions of cosmos that get encoded in those maps and see how understanding has changed. And you can correlate that with other things that are happening in society and culture. So, for example, in 1375, there is a map in this Catalan atlas by Abraham Cresques. All prior maps always had a godlike figure in them.
On the map?
On the map. 1375, for the first time, you actually do not have a godlike figure. I think what really drove that was an increased optimism about instruments, navigational instruments. The real search for explanations, as we know them, really started with Kepler. Till Brahe, all astronomy was naked eye. And so it was really after Galileo repurposed a telescope that astronomy has this real phase shift. And we start slowly moving into a more and more objective view.
Before we dive deep into this stuff, your own education has spanned 3 continents.
Yeah.
And so it would be interesting just to have a quick overview of what brought you to your current position in Yale and the various globe-spanning steps that you made on the trajectory to that.
I was born to parents who, our academics were in India. So bulk of my childhood was in India. I finished high school there. So this was the 80s, and my father had got me a Commodore 64 because parents are academics. They were always in and out for conferences to the US. So I had a Commodore 64, and before that I had a Sinclair ZX Spectrum. This, of course, completely dates me. But I had learned to program. It was very unusual for a kid to have their own computer at that time.
Anywhere in the world at that
yes,
stage.
Exactly.
Yeah. And to be able to get a Commodore 64 across the ocean, there probably wasn't a local dealer, right?
No. Dad brought it. And we had to troubleshoot it and fix it if anything went wrong, right? There was nobody who knew what to do with it. And so I learned to program. There was something about learning by doing that I was really captured with. That was so exciting. I could do so much more than just with pencil, paper. And, I was the usual kid. I found math easy. I found physics easy in school.
When you say you were a normal kid and finding math and physics easy, you mean you were a normal kid for future astrophysicists.
Right.
In your peer group, I'm sure that is quite normal, but amongst us civilians, that's a little less common.
Right. But, I loved books too. I loved fiction. I just loved a lot of things. But I was itching to do something. So my first break that really set me on the path to come to the United States started with a mentor that I had. There was this woman, Nirupama Raghavan, Dr. Raghavan, who had come and taken over the helm of the Nehru Planetarium in Delhi. She wanted to start off this public programs. And so I showed up on a public night and had a great time. And then I decided that I really liked her. And I decided I wanted to work with her. So
you're how old at this point?
I was 14. And so I went up to her and I said, okay, this is summer. Could I have a summer project? So I pestered her. She said, why don't you map the night sky? Because I had told her that I was obsessed with maps, which I was, terrestrial maps as well as celestial maps. She said, why don't you program and make me a map of the night sky for Delhi? In 6 weeks, I cracked the problem and I came back to her with a map of the night sky for that night. I just printed it out. And she thought, let me just test this kid, right? She said, well, this is great, Priya, but what if you move to Boston or Brisbane? What about the night sky? What are you going to do? You love maps. Don't you want a map? I said, oh, done. You just have to put the latitude and longitude of any place on Earth.
And out pops the map.
And it was not a laptop, right? So I had to go back home and I did it and I showed it to her. And so at that point, she decided, okay, now this is a kid that I do want.
That is a very high admissions barrier for mentorship at 14.
Exactly.
I mean, that's like applying to grad school. You practically had to submit a thesis to her, but that is a wonderful story. So she did become your mentor.
Absolutely.
And that was the beginning of your path toward astrophysics, I see.
Right. That was because, I did a project with her on sunspots. It was a sunspot high that year. So I built a camera to look at the sun, track the sunspots and so on. And I wrote a little research report thing. The International Astronomers Union in 1985 was in India, in Delhi. And at that point, I realized that I wanted an education that had a research component. So in India, unfortunately, research and pedagogy had gotten split institutionally. So you went to colleges or institutes and you just got foundational knowledge. There was no room to do research. And I knew about research universities thanks to my parents. And so I said, okay, this is what I want. And that's what brought me to America.
To MIT.
So I had to go to the United States Educational Foundation office in India. I applied to the usual 4 or 5 big places because they gave you full scholarships. So that's how I ended up at MIT. And MIT appealed to me because it seemed to have more breadth in the areas that I was interested in at the time.
Now, there were enough headwinds for women entering STEM in the United States in 2018. You entered STEM in India, which has got probably a wider gulf between the genders, in the 80s, which was quite some time ago. The passions that you had, I imagine with your parents who were academics, they delighted in that. But did you feel any societal or educational headwinds?
No. So strangely, the high school culture in India was fundamentally different from the United States in the sense that the cool kids did the hard stuff and you had to be smart to do the hard stuff. And that's what you did. It wasn't as gendered at all.
That's great.
What was gendered was the numbers, the demographics. So I was in the section of people who did focused science in high school. And there were 47 people in my section and there were 7 girls. So the demographics is something that one noticed, but I did not really feel that I was peculiar. The way in which I felt that I was different was I was driven in a very different way from even my classmates at the time, because the goal for this elite section was to get into the IITs.
For those who don't know, India Institute of Technology, there are multiple campuses. There is a national exam to get in. Results are published in local papers. It is a huge, huge deal and immensely selective.
Immensely selective.
Yeah.
And most of my class was set on that. And I was very clear I wanted to do basic sciences and I didn't want to do engineering.
And off you go to MIT, which has also got IT in the name. And then when you arrived, you were interested in robotics and all these different things. When did you find yourself focusing in on astronomy, astrophysics, cosmology, all these synonyms we can throw out?
Probably sophomore year became very clear to me that the thing that I really enjoyed most was physics and mathematics. And that computer science, I took this iconic class. I took the whole sequence. Somehow at the time, to me, at that stage, I couldn't see the room for creativity. It seemed so structured. I had to learn so much of that. Whereas I'd had a head start with physics. I had learned all this foundational stuff already. And
partly from your mentor and also in high school.
In high school.
Yeah.
Part of the curriculum. And somehow I felt that the capacity to do something on my own, I had more of that possibility for self-expression, if you will, with physics and math. And I signed up with Alan Guth, who is one of the founders of the theory of inflation. So I started doing a research project with him.
A quick interjection. We'll get to inflation in some depth. Yeah. We're not talking about economic inflation. We're talking about something that happened very early in the universe's history, which we'll get back to. But Absolutely. That was fairly early in the history of that field, or
1980s. Yeah, it was early-ish, and it was a very active area of research.
Was it still one of several competing theories, or was it largely accepted as something that almost surely happened?
The data was just coming in. So the first results from the COBE satellite measurements of the cosmic microwave background radiation and the measurement of the temperature differences across the sky to higher precision than ever had been done before, that was just coming in. And so the idea of inflation was getting some observational support. So, it was a very interesting, rich time for that theory.
Well, actually, this touches on something that we are surely going to spend time on. So why don't we pivot to setting very broad context here to talk briefly about the extent of the universe, its age, how far we can see in all directions, and how that ties to inflation, because this actually is a beautiful way to set context for our larger conversations about the dark places and forces of the universe, Absolutely. Which we will spend most of our time on, which are absolutely fascinating.
What is remarkable is that at this point, we have an incredibly nuanced understanding of cosmic history. despite a lot of big blind spots, which we're going to come to, these dark forces that essentially shape the universe. So we know the entire timeline of the universe. We know that the universe is about 13.78 billion years old. And we know that we had a very hot and messy start.
The Big Bang.
The Big Bang.
And its aftermath.
It's not really an explosion. I just need to add here that the Big Bang actually happened everywhere because that was the universe at that time. So it was essentially a period when the density was very, very high, and the universe was very, very hot. And after that really fiery stage, very soon after, 10 to the minus 36 seconds after that, there was a phase of very rapid expansion of the size of the universe.
And this is inflation.
This is inflation.
Yeah.
And it lasted for a very short period of time, down to when the universe was about 10 to the minus 32 seconds.
But the important thing is speed is astonishing. It was expanding at a speed much faster than the speed of light, which would seem to violate one of the fundamental principles of physics, except while nothing can travel faster than light as far as we know within space, there's nothing that says space itself cannot expand faster than light. And that is indeed what happened. How much faster than the speed of light?
3 times.
3 times faster.
Yeah. You're right. That sounds counterintuitive, but at this stage of the universe, there was no matter. So it's really matter that cannot travel faster than the speed of light, right? Space itself was expanding very, very rapidly. But then it stopped. This period of inflation stopped. And then we had this long epoch in which the universe was expanding, not at this exponential rate anymore, but at a slowed down rate. And the universe was expanding and cooling simultaneously. But there was a period of time where the composition of universe is really dominated by this early radiation.
As opposed to matter. Yeah.
Then you start sliding into the matter-dominated era.
Because it got cool enough for matter to start cohering.
For bits of atoms to coalesce and to start forming full atoms. And then you moved into a matter-dominated phase.
How long was the radiation-dominated phase?
Between 300 to 400,000 years after the Big Bang.
And when do the first stars light up?
Much later, because there are lots of physical processes that really need to happen. So one thing that inflation, we believe, does, for which we don't quite have conclusive proof yet, is that when we have this sea of matter that is generated in the universe, there are some small fluctuations that are imprinted on the sea of matter. And these fluctuations, we believe, are set up during the inflationary epoch. It's almost like water waves and you're sloshing around. But what is different is these are waves which are heaps of matter that are collapsing, condensing, and forming piles. So gravity aggregates these small fluctuations, these little lumps of dark matter. It turns out that it's dark matter, and coalesces them and forms them as little lumps that somehow get massive enough that they are no longer torqued by the expansion of the universe. Because remember, this background, the universe is expanding all the time.
So they get massive enough that they start to clump together and have a gravitational field that overcomes the expansion of the universe, so they can start becoming bigger and bigger things.
That's right.
Bigger and bigger aggregations of matter. And is that what ultimately starts cohering into celestial objects?
Absolutely. But you need ordinary matter on top of this, right? So we have ordinary matter that is dispersed. And once these cocoons of dark matter get massive enough and they have decoupled from the expansion of the universe, held by their own gravity, they start sucking in gas, so it's hydrogen.
So we're obviously now talking about dark matter, which is a fascinating topic and one of the two areas you've focused on the most in your research thus far.
That's right.
And correct me if my layman's English is a little bit off, but the dark matter has created, in a sense, a scaffolding that allows the normal matter to start collapsing and forming stuff.
That's the kind of analogy that we all often use, astrophysicists. So you have this scaffolding, the places where the scaffolding meets, that's where you have the cocoons, and that's where you form the galaxies. And the scaffolding itself are streams of dark matter that keep flowing in and supplying these regions. So there are these flows.
There's flows within the scaffolding of the dark matter particles.
Yeah, dark matter particles. And dark matter is this peculiar class of particles that neither emits, absorbs, or reflects light. The only thing, luckily, that dark matter does is deflect light because it actually has mass and it's matter and therefore has a gravitational field.
What is the ratio of dark matter mass to ordinary matter mass? It's about 6-7 to 1.
Yeah.
Is that right?
10 to 1 even
10
in
to
some
1 even,
places
yeah.
in the galaxy, for example.
So there's a lot more of that stuff out there, which we can only detect by the way it bends light waves.
Or it actually impacts the motions of particles because it's gravity.
Right, yeah.
So there are just two ways. One is the impact on the motions of particles in their vicinity, the speeds, because of the gravitational field, they could speed stuff up.
Yep.
Or the bending of light. And they're both indirect ways
Yep.
to figure out how much dark matter we
But
have.
that evidence is overwhelming because dark matter plays such an important role in the early formation of the galaxies. So now this ordinary matter that we're more familiar with starts to cohere.
Fall into these cocoons.
Into these
halos.
cocoons and these halos, which allows the formation of stars and galaxies, correct?
That's right. And the first stars form after this gas falls in, cools a little bit, gets denser and clumps and gets denser and denser, and eventually it ignites.
It ignites because some conglomerations of ordinary matter are so dense that nuclear fusion begins.
Stuff, yeah.
And that has got the great title or the great name Cosmic Dawn, am I correct?
That's right.
And that's when the first stars start lighting up. When is that after the birth of the universe?
Roughly about 350 to 370 million years after the Big Bang.
Into the 13.8 billion year history of the universe.
Yeah.
So fast forwarding to today,
Yeah.
when we look out, we can see a bit under 14 billion light years in all directions. And the naive view that might come from that is, oh my God, nothing travels faster than light. The universe is X years old. I can see X light years in all directions. We must be right in the center of this thing. And that would be a naive view, would of course be wrong. And the thing that explains the fact that we're not smack in the center is inflation. That has enabled things to stretch much, much further in
And
all
also
directions.
the fact that when you start out with the Big Bang did not actually happen in one place. It happened everywhere.
Right. To my own layman's mind, when I started hearing about inflation some years ago and started trying to wrap my head around it, the proof point that ultimately resonated for me, again, I'm going to use silly terms. If I look to the left and I can see 13 point something billion light years, and I look to the right and I can see 13.8 something billion light years, that furthest point on the right, the people there, if there are people, would be completely unable to see the furthest point on my left, because that's more than the history of the universe apart. So isn't that interesting? And if that's the case, it would seem to imply that those people on the right and those people on the left themselves can see things that I can't see. So that tells me that our ordinary universe stretches far, far beyond my own gaze. But the other thing that's fascinating is that the non-absolute zero temperature of the universe on both the right and the left, those two things, in theory, never could have touched or interacted with each other. They're beyond each other's light hemisphere.
But I think the key thing is the fact that they agree
They're
to
identical.
the fifth decimal place.
They have the identical
Coordinate
temperatures.
yeah.
And so that suggests they simply must have had an equalizing moment because they were obviously equalized.
Yeah.
And that really seems to make an overwhelmingly powerful case for inflation. Now, one of the other things that's not necessarily intuitive is the more distant an object is, in a sense, the older it is, or more accurately, the older our information about that object is, because if we're looking at something on the edge of the observable universe, 13 point something billion light years, by definition, that light started traveling 13 point something billion years ago. So we're not seeing it as it is, we're seeing it as it was.
Absolutely. Therefore, when we go look out into the night sky, we really are seeing objects when light left them. So what they're doing now, who knows? So in a way, we are constantly looking back into the past. And so we have these snapshots and we are seeing these objects that are being created.
Now, one of the things that's fascinated me since I first read about them, and I was probably 11 or 12 when I did, are something that's very significant to your research and very germane to this conversation, quasars. When I was a 12-year-old and was reading the local paper, there was this really fabulous long article about astronomy. And they talked about the fact that there were these brilliant beacons on the edge of the universe in all directions. It's like these pinpoints of light that almost defined the edge of the universe. There's nothing past those quasars. And that notion intrigued and haunted me until years later I started thinking, wait, no, there's this age thing. So maybe these quasars are things that happened really early everywhere. And that is indeed largely the case.
Yeah. So quasars are incredibly powerful, bright objects, cosmic beacons, lighthouses, if you will. And they're so bright, and therefore we can see them out to the farthest reaches. Quasars are powered by the accretion or infall of matter into assembling black holes. And this process of being pulled in by the immense gravity of a black hole heats up the gas as it's forming, and it starts to glow. And that's what we end up seeing.
Because it's falling in so fast. The energy has gotten so high that even though this is not a star we're seeing, the gas starts to phosphoresce. It starts to emit light.
Yeah.
So these quasars are not merely just any black hole forming or feeding. They are a special kind of black hole, which is supermassive, right?
Supermassive.
And this is something that tended to happen early in the universe's history, which is why they tend to be on the edge of our seeing. That happens early in the formation of a galaxy, when there's still a great deal of gas around that hasn't yet been claimed by different stars. And the quasar is, generally speaking, the formation of a gigantic black hole that sits in the center of the galaxy. And we've got one ourselves in the Milky Way, correct?
So the black hole at the center of the Milky Way is 4 million times the mass of the sun. We believe that these supermassive black holes actually sink into the center of galaxies.
It sink almost in the way that if there was an impossibly heavy item or element on Earth, it would sink into the center of the Earth. Gravity would draw on it until it got to this point of stasis in the middle.
It's an interesting dynamical process because it's kind of sloshing through a collection of stars.
And it's devouring stars on the way.
Right, devouring stars on the
way. If it gets close
way.
enough to a star, it can start eating that thing up.
Absolutely.
Now, given that stars are much denser in the center of galaxies, why is it that a 4 million solar mass black hole in the center of the Milky Way, why doesn't it keep on eating? Why doesn't it just suck in all the neighboring stars and get more and more and more of these stars and devour more and more? What gets it to a point of stasis where we get to still have a galaxy and it doesn't just get everything?
It turns out that the black hole, immense as its gravity is, has a very small region where its gravity dominates.
So let's talk about the basic physiological characteristics of black holes.
Sure. So they have a sacred boundary, this boundary called the event horizon, which is proportional to the mass of the black hole. And this is the region within which once anything with matter, even light, gets in, there's no way out.
That's the point of no return.
A point of no return. The way to think about it, when we launch satellites from the surface of the Earth, we need to boost the rocket to these very, very high velocities to escape the gravity of the Earth. So there's this idea of escape velocity.
And that is quite possible on Earth. It even would be possible if you were able to put a vehicle on the sun to escape the sun's gravity. So the event horizon is at the point at which you would have to be going faster than the speed of light, which is impossible to escape the black holes. So that is the point of no return. Now, this fascinated me when we had one of our earlier conversations. I had never really had much of a notion of how short of a radius that there really is. So the one in the center of the Milky Way, it's 4 million solar masses.
So the radius of the event horizon is about 3 million miles.
That's nothing. That's like a fraction of our distance. It's a 30th of our distance from the sun. This helped me understand why it's not going to continually feed on stars, because even with the greater density of stars in the center of the galaxy, they're not 30 million miles. That's like closer than Mercury is to the sun.
Yeah. So it's really tight.
Tiny,
very tight.
Now, let's talk briefly about these smaller black holes, where they come from. So we have the giant ogre in the center of the galaxy, but these smaller ones are one of 3 end states for stars. Could we briefly tour the 3 end states that stars end up in, and then talk about those lucky or unlucky ones that get to be black holes at the end of their lives?
Right. So I think your birth determines your destiny for stars. So if you are born as a star that is less than about 8 times the mass of the sun,
our sun's cohort.
Yeah, a sun's
roughly
cohort.
8x bigger to maybe 8 or 10x smaller.
Yeah.
The sun's cohort. Yeah.
The sun's cohort. So the stars are powered by fusion, and there's this delicate balance between gravity and pressure from the radiation from this plasma that's in the center.
The radiation wants to push out, the gravity wants to pull in.
There's this tug going on, and it's a pretty delicate balance.
While this fuel is getting burnt that's
out,
creating that outward pressure.
Absolutely. Yeah. And so as soon as you start exhausting that fuel, you no longer have that pressure, and gravity starts to win. And so there are these periods where you have these violent oscillations.
Sunquakes almost.
Yeah. And then you start to collapse. And then when you collapse, if you are in this cohort, then you would end up as a red giant star, and then you would end up as a white dwarf. Explosion. So you spew out a lot of the matter, so it's gassy, a lot of radiation. Then you end up as a very compact white dwarf.
And so that is the sun's fate.
That's the
inevitable.
sun's fate.
Yeah.
And so our sun is going to go there in about 5 billion years.
And then once it becomes a white dwarf, it's cooling and cooling. These are cinders in a sense.
Yeah. And they'll be cooling forever. They
Forever,
are very
yeah.
long time scales. They're going to outlive anything in the universe. So sitting there cooling away.
Will they be visible after they enter the white dwarf phase for a period of time?
For a period of time, but not for long.
But not for long. Now, let's talk about the bigger guys, the ones that are 8x the size of our sun
and beyond.
How far beyond does it get? Do you get 100x?
We think that the first episode of star formation, because of the simpler chemistry in the early universe, within the first 3 minutes, you made all the hydrogen, helium, up to lithium in the periodic table. And then you had to wait for the nuclear reactors in the centers of the stars to fuse to make all the higher elements.
So the biggest stars could get bigger in the early universe?
So in the early universe, we think that you could even form a star that was simply 100 times the mass of the sun, maybe 150 times the mass of the sun.
But we don't see that now.
We believe that when the cooling chemistry gets to be more complex and you have a lot of metals that facilitate faster, more rapid cooling, that you would fragment faster, so you would make smaller stars to start.
But if your 8x or bigger, you're going to blow up in a more spectacular way than the sun blowing.
Once again, that delicate balance is destroyed, then you collapse and you form like a massive red giant again. So you have this big envelope, you blow off, you have a violent end, and you leave behind one of two possibilities. You could either be a neutron star or you could end up as a black hole. And the difference between the neutron star and a black hole is really how densely matter is packed. Neutron stars, they're really at the limit. And once matter gets packed much, much more than the neutron star limit, gravity completely overwhelms it.
And it becomes a black hole. But the neutron stars themselves are plenty weird, aren't they?
They're super weird.
First of all, do they emit radiation? Or do they look like pinpricks of light if you're close enough to them?
Yeah. You would see them. But more importantly, you see a class of these crazy neutron stars that are rotating really fast. 700 to 800 times per second.
Per second.
Yeah.
This massive object is spinning at that rate.
Yeah.
That's not all neutron stars. That's just some.
That's a range. Yeah. Those
are the pulsars?
Those are the pulsars. Yeah.
Yeah. And they're spinning because of some property of the explosion, kinetic energy.
Yeah. So it's by birth.
Yeah.
So they're carrying the spin, which is a remnant of the creation process. And also we believe that neutron stars probably have huge magnetic fields in them. But what is intriguing about pulsars is that their spin times are incredibly accurate. They hold their spin incredibly well.
They're very, very regular.
Very, very regular.
Yeah.
They are the equivalent of our atomic clocks.
Yeah.
You could use them as timing devices.
How many would you ballpark are in the Milky Way?
We could have 1 million or so.
A million or so. And how many post-star collapse black holes? A similar number?
We believe that you could have produced up to 1 million tiny stellar mass black holes as well.
So there could be 1 million-ish of those, and then the monster in the center of the galaxy.
Absolutely.
And then just a quick detour, because we're talking about these different types of dwarves. Red dwarfs are pretty fascinating too.
Yeah.
Because they're going to last for trillions.
Of years. Yeah.
Trillions of years. Which is to say that the universe at its roughly 14 billion year age, the oldest red dwarf in the universe, it's not even 1% of the way into its history at this stage.
Yes, right.
Now, these are small fry, right?
Very small fry.
And they're
really insignificant in terms of the mass budget or for any of this work that I do in terms of either the mass dark matter inventory, the matter inventory.
I can tell they bore you to death just by your tone. But are they 1% the size of the sun or even smaller than that?
Even smaller. They're very compact. Extremely compact. Yeah, about 1% of the size of the sun or even more compact.
And super abundant though, right?
They're littered everywhere.
They're everywhere. These completely tiresome, tedious, uninteresting, long-lived, they don't know when to quit. They're just going to go for trillions of years, boring everybody. Right. So let's get to something much more exciting.
Right.
Let's get to the ultra-massive black holes. And this fascinating notion that you have created and named, and which may well be proven if the James Webb Telescope would ever get into orbit, called the direct collapse black hole. This is such an exciting notion.
Any black hole that is above 5 billion times the mass of the sun, call them ultramassive black holes.
And just to pause again, these orders of magnitude are so astonishing because a black hole that's formed by a supernova would be 1 or 2 times the size of the sun because so much of that star's matter would have been blown off. It might have started at 10x the sun, but by the time it's a black hole, it's maybe 2x.
Right.
This thing in the middle of the Milky Way, oh my God, it's 4 million. Now we're getting into many billions, like many orders of magnitude bigger.
So the first point is that when you have something that is 1 billion times the mass of the sun, that is being fed and is seen as a quasar way back when the universe was, say, 800 million years old.
So this is something that would be on the edge of our seeing, maybe 13 billion light years from us.
Right.
We're seeing this incredibly bright thing.
Yeah, very bright thing. And we just finished talking about how do you form the first stars, and you look at the timeline. If the origin for that monster were to be the end state of one of the stars that first formed, then there's a real timing challenge in terms of how to feed one of those to grow it so rapidly within such a short span of time. It's kind of tight to start with the remnant of a star mass seed black hole and grow it up to 1 billion times the mass of the sun in such a short period in the early universe.
So it's tight, not geographically or expansive space, it's tight in time.
It's very tight in time.
We're seeing masses out there that simply should not have had time to form.
That's right.
That early in the universe.
If you find one object, you can say, oh, that freak object happened to be the lucky one. It got fed the right way, right conditions. But increasingly, we are finding a population of them. The demographics are showing us now there has to be some natural pathway. So in 2005 and 2006, with one of my postdocs, Giuseppe Lodato, we worked out that if we were able to construct cosmic conditions where you could have gas that would settle down into, say, a disk of gas, we just need to find conditions where this gas disk would somehow not fragment. And
so
would just be swirling.
And it would skip the star phase entirely and become a black hole without ever having been a star. And so thus the terminology that you came up with, right?
That's right. Yeah.
Direct collapse black hole.
Right.
Yeah.
And so we want matter to flow into the center to seed the black hole, to make the seed black hole, which means you have to lose a lot of the rotation. So you need some instability that would rocket and push the matter into the center. It's really like if you're in a bathtub and after you've soaked, you pull out the plug.
Yep.
And you see the water like really siphoning in really fast into that vortex. It's exactly that. It's the same instability that we set up in the early disk. And we noticed that you could get a lot of matter down very rapidly, and it would be so compact and dense that it would inevitably form a black hole. But as an astrophysicist, it's not just about ideas, right? And ideas and imagination. It's that, but then these have to be translated into predictions that can be proven or disproven.
And we will be able potentially to discern this, right, with the James Webb Telescope.
So one interesting thing is that this spectrum, right, all of this energy is going to come out between 1 and 30 microns in the infrared. And this is precisely the window that the James Webb Space Telescope is going to open out for us in the universe. And it's going to be the highest resolution infrared detectors, infrared eyes with which we have ever looked into the universe.
And Hubble, our current space telescope, simply can't look at those frequencies, correct?
That's right. It doesn't have the filter set to look at that. So the Hubble can detect ultraviolet, the bluer and the redder, but it has exquisite resolution in the blue.
Hubble does, yeah.
Hubble does.
So could you give us a quick primer on what James Webb is, when it's hopefully going to go up, its specs compared to Hubble, et cetera?
Yeah. So the James Webb Space Telescope is actually going to be just like the Hubble, but with the same resolution that the Hubble has in blue light, in infrared light.
Oh, really? So the mirror is about the same size?
The mirror is roughly the same size.
Really? I didn't realize that.
But it's a very complex geometry for the mirror. And the sun shield needs to open up into an umbrella. And that has been the current hitch with the launch date. And the current anticipated launch date is March 2021.
2021? So it just slipped again?
Yeah, it slipped again to 2021.
When did it slip?
Just like a couple of weeks ago.
Oh, gosh.
It's an exquisite telescope. And it's going to allow us to peer farther and deeper into the universe, because in the early universe, there was a lot of gas and dust. So when stars form, when black holes accrete, a lot of the energy comes out in the blue, in ultraviolet, but then it's not able to escape because of this dust. So it scatters off.
It gets absorbed by the dust?
It gets absorbed and reabsorbed, scattered back, and it gets rescattered out into longer wavelengths.
So if we can see those longer wavelengths, we can actually see further back into the history of the universe, and we can also see these super distant objects, which is what would be causing a direct collapse black hole.
That's right. We'll finally have the capacity to look back into the epoch in the universe where these direct collapse black holes would
have happened if they happened.
If they happened.
Now, to explore a couple of the more wild and woolly topics, Inflation allows us to envision a universe that is far, far larger than 14 billion light years to the left and to the right, to use my silly terminology from before, far bigger. Is there any notional limit to how far the universe could extend, to how extensive inflation might have been? We know that it was 3 times the speed of light for a very brief instant, but the question then becomes, as you pointed out, that was happening everywhere. How extensive was everywhere?
We don't actually know if the universe is finite or infinite.
But infinite is on the menu. Infinite is a possibility.
It's a total possibility. It's permitted. But the motivation that I like for the idea of other possible bubble universes actually comes from a slightly different argument. And the argument is that in order to describe the past, present, future of the universe, it appears that in the current framework that we have, you just need 6 numbers. The expansion history of the universe, the coupling constant alpha, the mass of the electron, the Hubble expansion rate. So there's just these handful of numbers for basic physical constants, which can be measured. And the point is, if these 6 numbers were different from what they are, and some of them by a minuscule amount, right? Then you would find that we wouldn't be here.
There would not be a universe that would create stars and therefore us.
Wouldn't have this familiar flow of structure formation as we know, and therefore we wouldn't be here, and so on and so forth. So one way to think about this, which to me is a comfortable way to think about it, is maybe it's the combinations of these 6 numbers will give you a whole range of infinite number of viable universes. We just happen to be living in one that has this particular combination, and that therefore you could have instantiations, an infinite number of them.
Not created by inflation in our universe, but in a sense parallel.
By other separate inflationary bubbles. Because it's infinite, you could also have a universe in which Priya is interviewing Rob.
Of course.
Rather than Rob interviewing Priya.
Or Rob's interviewing Priya, but said one syllable slightly differently. Now, that possibility also comes into focus if we have an infinite universe caused by inflation within our own universe.
Right. You could conceive of it in a bunch of different ways. I mean, you could think of us as being one isolated bubble in the corner of what could be one bigger universe, or you could think of it as different bubble universes. So this is this concept of the multiverse.
Yeah.
And obviously it's not testable at the moment, but as I said, I believe in the multiverse. It's just appealing. And the reason it's a bit tricky right now is we don't know how to access any other bubble. By definition, you can't directly.
Yeah.
So we are limited by our light horizon. So we really can't get any data information from beyond that. But who knows, right? We might be able to come up with ways to test this idea. In 1543, when Copernicus reordered the Earth and the Sun, he could have never imagined that later we would have actually flown 2 satellites, Voyager 1 and 2, that would leave the solar system, right? So the path of future science cannot be predicted.
Now, another wild thing to contemplate, what do you suppose goes on inside these objects of your study, black holes? I mean, if you were unfortunate enough to take your space Tesla and take a wrong turn and cross the event horizon, what do you believe you would encounter? And I know it's by definition speculative, but where does your imagination take you when you think about these things?
In terms of the physical effects, we know what the overwhelming effect of that immense gravity is going to be, right? That even for something as finite a size and as small as us, like a human being, the difference in the gravitational pull between my hair and my toes is going to be so intense that I would just be torn apart.
Because the closer you get to a gravitational center, the higher the gravitational pull.
Yeah.
So if I'm standing here on Earth, in theory, there is a slightly less gravitational pull on my head than on my feet. But that's
minuscule.
It's minuscule. Let's assume then that there's some way to make a very hardy, tiny nugget that goes in there, whether it has some conscious experience or it's a fabulous AI or it's just a recording device. What do you think is in there?
This is an unsolved problem at the moment. Of course. Right?
I'm a science fiction writer. You had to expect this question.
That's right. Yeah, of course. There's a beautiful analogy that Stephen Hawking came up with. Suppose you had the Encyclopedia Britannica and I wanted to look up the capital of India. I wanted to read about India. So I open up and I read all about India, population stats, whatever. Then I close it. And now I put this encyclopedia in a box where nothing can leave. And then I burn the encyclopedia.
You heat the box up to Fahrenheit 451 and
whatever.
It combusts. It's nothing but ashes in there as far as we know, but the box is closed.
The box is closed, so all the ashes are in there, right? Which means that at some level, my encyclopedia is still there, right? My encyclopedia is there.
Because it is a sealed box. Nothing has gotten out.
Nothing's gotten out, right? However, I no longer know how to use it as an encyclopedia. I don't know how to look up anything. I also don't know how that information that I knew was in there, because I checked it myself just a little while ago. I no longer know how it's stored, because I knew earlier it was printed on paper and with this ink and that paper. Now I no longer know that, right? So when matter crosses the event horizon, we don't know how the properties of what fell in, be it a sentient being, plant, nugget, what have you. We have no idea how the properties of that thing that fell in are retained. And we also no longer know how to recover that information.
Well, we can't recover it because it's beyond the event horizon. So we can't yank it out. That, by
but
definition.
How it's actually stored there, is it stored there? Hawking famously changed his mind on this. So first he thought you couldn't recover anything from a black hole. And then now it's not so clear, because we don't really understand what happens to the properties of things that fall into black holes. And it's often variously called information. And it's just that we don't know how it's encapsulated.
It's like the neutron star is crazy dense, right? Like a teaspoon of a neutron star would weigh tons, something crazy like that. So there isn't a notion that it's like that, but denser still.
The reason for that is a neutron star is really the limit that we can imagine that
packing matter.
Of packing matter, that of ordinary matter that we know.
Yeah.
And because the black hole is beyond that, right, that notion has to collapse. So you really have to start thinking about geometry. The tricky part with the black hole, intriguing as the event horizon is actually the singularity.
Yeah.
That's encased in it, right? And that's the real singularity. So this event horizon is an artifact of the peculiar geometry that this compact, intense gravity generates, but the singularity is real. And this is a place, it encases a region where our understanding of physics, our formulation of mathematics, everything fails.
And is this considered to be an infinitesimally small point? Or when we think of the singularity, is it the size of a golf ball? Do we have a notion of it having any geometric extent, or is that just the wrong term?
Yeah, it's just the wrong way to think about it.
Yeah.
One just thinks about it as an asymptotic place.
Let's talk about something weird now, because that really wasn't weird enough.
Right, that's not weird enough.
Let's get back to dark matter. One of the giant contributions that you have made is direct collapse black holes, which we've talked about. Another one is in the mapping and measuring of dark matter. Talk us briefly through a day in the life, as far as we know, of a dark matter particle. What's causing it to go from point A to point B? What are the nature of its interactions, if any?
It's streaming along in the universe. And every time it gets close to a gravitating body, like a galaxy or our Earth, for example, their paths get slightly deflected because of the gravity, so they get sped up.
So they do, quote unquote, feel gravity.
Absolutely.
And what speed are these critters moving at? The fact that they can be sped up by gravity means, by definition, they're not moving at light speed like electromagnetic radiation.
No. These are cosmically extremely lazy particles. They're like ambling through the universe at speeds of about a couple of 100 kilometers per second.
Which is tiny compared to the speed of light, which electromagnetic radiation moves at. That's about 1,000th of the speed of light.
That's right.
But very fast in comparison to anything we've ever done.
Yeah. For example, right, to give a sense of 200 kilometers per second really means, in order to launch a rocket to escape gravity from the surface of the Earth, we need to launch it at 12 kilometers per second. That's what we've been doing.
So they're moving at roughly 10 times the speed of anything that we've created, but still about 1,000th of the speed of light.
Absolutely. And to get a better sense, escape velocity from Earth's gravity, that is actually about 30 times the speed of sound. So we're talking Mach 33.
So zippy compared to us, very pokey compared to much of what's out there. And they do have some influence from gravity.
Right. They do feel gravity because they have mass. So they will speed up when they reach bodies that are massive compared to them. So dark matter particles that come towards the Earth, for example, will be sped up when they get closer to us.
And although much about them is mysterious, we do have a certain sense for their abundance. If we take the median size that they may well be, roughly how many dark matter particles are likely to be passing through me at any given moment or any given second, let's say?
Right. So if I say it's a 10 GeV particle, remember there's an uncertainty in the mass range. I'm just picking like one random number for illustration. Then it turns out that there are between 10 to the 10 to 10 to the 11 dark matter particles that are passing through us every second.
So that is 10 billion, to put it into civilian speak, non-exponential speak. 10 billion of these things are passing through us at any second. So there's plenty of them on Earth to be detected at any given moment.
You might ask, if this is such an enormous rate, why haven't we found them yet? It turns out that the key is not just the number, right? It is whether we can stop them, whether we can hold on to them. And it turns out we don't know how to stop them because they don't interact with anything. So we don't know how to actually slow them down, hold on to them. The only force other than gravity that they experience is likely the weak force.
The weak nuclear force.
The weak nuclear force, which is enormously weak. So despite the number of particles that we have, the flux as it's called, going through, it's the peculiar nature of their inertness that prevents us from capturing them.
So to get back to dark matter's function in the universe, what exactly does it do?
As we were talking about earlier, right? Dark matter settles into these cocoons in which galaxies form, and then structure in the universe aggregates, and you form bigger and bigger objects, more and more massive objects later on in time from the coalescence of smaller objects, the merging of smaller objects.
And that coalescence is, in a sense, shepherded by the scaffolding of this dark matter.
By dark matter.
And without that dark matter, galaxies simply wouldn't have formed. It needed to perform this shepherding function.
Absolutely.
And could we talk briefly actually about gravitational lensing? And that was an early proof point, wasn't it, of dark matter?
Central to the understanding of gravitational lensing, which is just the bending of light, is this notion of space-time. The fact that we exist on this four-dimensional sheet, nothing above it, there's nothing below it, so we are all embedded in it. The entire universe is embedded in this sheet. And any matter will cause a divot in space-time. So all galaxies have their little potholes and divots, and space-time is just pockmarked because we have a lot of matter in the universe. So light from a galaxy would have to traverse every little divot, every pothole to reach us. And light actually carries the imprint of every little pothole that it has traversed in terms of the shape that we see for that original galaxy. See, the galaxy had a projected shape that was a circle. By the time the light passes through a couple of divots, what we end up seeing is that the circle gets deformed, elongated, and you would end up seeing an ellipse.
Or we also see multiple images.
When things really line up. And then what happens is that if you have a very deep divot,
created by some very massive object.
By very massive
which was a galaxy, perhaps.
Or a galaxy cluster, which
is
1,000 galaxies held together by dark matter.
Yeah.
So then that light gets split into many. So you end up seeing many copies of the same object, where in reality you have one object, one galaxy, and you see multiple images of it.
You know it's the same thing because the spectrum is identical, and if you got into a granular enough level, you would see the exact same patterns of darkness and brightness and light. So you literally see multiple images.
Except that those different images, right, because you are split, light has traveled a different path lengths.
Oh, right. So some of it might have traveled a little further.
So
some
there
of it
could be a time delay.
There could be a time delay. Interesting. But it was when we first started seeing some of these split galaxies that people were able to make calculations about how much mass must have caused that diversion. And that's when it became clear that there had to be this immense dark matter.
Absolutely.
Because it would require so much more mass than was discernibly visible within the massive object that was causing this lensing, this breaking.
Right.
So that was early evidence that
That's very early evidence.
Yeah, that this dark matter is real.
That it was real. But we really needed the exquisite optics of the Hubble Space Telescope to detect not just these multiple copies, but also these extremely sheared, mangled shapes, these really stretched out shapes, these lensed galaxies, because of the strong distortions from traversing these divots. So that work that I pioneered, and it's standard process now, is to solve this inversion problem.
Now, let's imagine a freestanding galaxy, because that's just a little bit easier to wrap one's head around. Where would the dark matter particles be densest? Would they be densest in the center of the galaxy as the massive black hole is? Would they be drawn to the center because of their mass? Or would they be densest on the outside where they're creating this cocoon and shepherding the normal matter on the inside?
Right. So they are densest in the center.
In the center.
Absolutely. And they get sparser and sparser as you go out. but they extend to well beyond where the light is, 10 times almost beyond where the light ends.
Wow. So it's almost like the Oort cloud to our sun versus planets. It's way outside.
What's interesting in the innermost regions is that dark matter settles into a very, very dense distribution in the center. However, the ordinary matter is denser than the dark matter in the innermost regions of a galaxy because dark matter does not collide. The dark matter candidates that we believe describe all the statistics of the clustering, the scaffolding, have to have a very peculiar nature, that they need to be collisionless so that they don't actually collide and go thwack. They kind of graze past each other and they eventually coagulate.
But they don't interact with one another. So it's more like a sand dune than a bunch of sticky particles. Whereas normal matter is more like a bunch of sticky particles that's going to clump.
Right. So when you have normal matter, it can actually collapse, collide, condense even further. Because it collides, it has pressure, and it can condense even more. So you can pull in a lot more ordinary matter into the centers of galaxies.
What attempts are we making now to detect them, and what are our prospects?
If they would just go past heavy nuclei, we could see some nuclear recoil.
Heavy like uranium, plutonium?
No, xenon. So inert stuff. So we have these large underground vats of xenon. And the idea is that you're waiting around for a dark matter particle to go and jiggle the nucleus.
And we're watching that xenon carefully enough that if anything gets jiggled, we're going to know about it.
Including a truck driving up the highway or whatever.
Nothing like a false positive to make an experiment exciting. Yeah.
So it's a very challenging experiment, but no events, no detection so far.
None yet.
None yet. If it's on the light end, if we had a very, very powerful magnet, right, like 8 Tesla or something, that would then cause these axions to become photons, to convert into photons.
And then seen.
Are
those experiments underway?
There are a couple of experiments underway where they would give you photons in the microwave wavelengths. And so ADMX is an experiment that's out of Washington State. And at MIT, they have a new experiment called Abracadabra.
What do those mechanisms of experimentation look like?
They're not huge. They have superconducting magnets. They're like room-size experiments.
So is it possible that a detection could come along any day now?
It could. I'm very optimistic because if you take the case of the LIGO experiment, right? This recent detection 2 years ago
of gravity waves.
Gravity waves from stellar mass black holes. They were looking for about 40 years and they didn't see anything.
40 years?
The experiment. But they knew that they were improving the sensitivity over time.
When did the ultimately successful instrument launch for LIGO? When did they switch that sucker on?
The day they switched the sucker on, like practically to the day they detected the first event. Right?
The minute they opened it. Right? So it's just a matter of getting the right instrument.
There are lots of uncertainties in these things, right? So once again, they didn't know how far down in sensitivity they really needed to go. Because it depends on the event rate. How frequently they happen so that you would see the tip of the strongest event. And that was uncertain. Yeah. But the minute they hit the sensitivity limit, boom, they detected the first event, right? So who knows? I mean, it could happen. I think the thing that I most would love to have in my lifetime, without particularly elongating my lifetime by artificial means, is the detection of the collision of supermassive black holes in the universe with the LISA satellite. So the Europeans are going to launch a satellite, which is going to be like the LIGO system, these 3 detectors in space. That's what you need because the frequency of gravitational waves emitted by the merger of supermassive black holes in space is much lower than LIGO. And you need to be in space in order to detect that.
So LIGO detected 2 star-sized black holes.
Yeah, 20, 30 times the mass of the sun.
Colliding with each other. But if it was galactic core black holes colliding, you need a different instrument, listening at a different frequency effectively. Yeah. And LISA will be able to show us that.
LISA will be able to. And I'm on the NASA LISA science team. Very excited. So I would want to see that event.
Why is that? Would we be able to learn things from that event that we don't currently know, or would that event confirm something that we suspect but don't know for sure?
Well, I think it would ratify this entire picture of the assembly history of black holes over cosmic time, because that instrument could see supermassive black hole collisions almost out to when the first stars form. So, and that will stand to ratify the whole picture that we have of how black holes grow. So now we believe that black holes actually grow in 3 different ways. Once they form, they feed gas. So that's accretion. They could also grow by just colliding with each other and producing gravitational waves. And then we believe there's an intermediate thing where the collisions between galaxies could just trigger an accretion episode. And we think that you could have these 3 feeding modes and 3 kind of mass enhancing modes. And so Lisa would help you test that.
So it's time that we finally started talking about something weird, I keep saying. So let's get to the weirdest and most mysterious thing and most abundant thing in the universe, dark energy. Could we go through the cosmic inventory just to put all of this in perspective? What is the composition breakdown?
Our entire universe is composed of 3 things. So first, we have this very mysterious component that we call dark energy. We don't know what it is. We just merely call it energy because it powers the accelerating expansion of the universe, which we have measured. And then there's 26%, which is dark matter. And then there's everything that we are made of, everything that we are familiar with, everything in the periodic table, everything that's emitting light in the universe. That's a mere 4%.
So it's literally 1/25th of the universe. And some of that's in black holes, which we only faintly understand, although that's a tiny percentage of it.
But what is incredible is that with knowledge of this one tiny sliver of the composition of the universe, we have had the capacity to figure all of this stuff out. I think that's fascinating.
It is fascinating, and it's a triumph. And whenever something comes in that is immaculately congruent with theory, such as the Kobe satellite map, it has to be, or the dark matter maps that you've been involved in making. And hopefully when James Webb gets up there and starts peering into the infrared, evidence will emerge for direct collapse black holes. There's got to be something electrifying when these seemingly mad theories are just bullseye. But at the same time, there's something arguably even more electrifying when there's a yawning gap that's been discovered.
Absolutely.
But so to get to dark energy, tell us what we actually know, if anything. I mean, we know that there is a force that is pushing the universe apart, that's causing it to expand at an accelerating rate. And that thing we call dark energy. And that's about it, right? I mean,
that's about it.
That's about all we know.
One idea that is particularly appealing, and the observations are in line at the moment with this conception, is that space itself could have some kind of ground state energy, vacuum energy. And therefore, it would be a constant component. And this would be a component that would stay constant as the universe transited through inflation, radiation-dominated era, matter-dominated era, and bingo, about 4 to 5 billion years ago, it starts to dominate.
Is that what's called zero-point energy?
Yeah, the ground state energy, vacuum energy.
So that is a candidate for
That is a candidate, and that would remain constant in time. That's a prediction. If it were that.
If it were that.
And the current observational limits and constraints and measurements of dark energy are consistent with this component having been constant over cosmic time, but having taken over in terms of dominating the dynamics of the universe around 4 to 5 billion years ago. That's because matter has gotten diluted enough because of the overall expansion of the universe that this piece starts to become the dominant piece of the universe. So the key property of that vacuum energy, which is called the cosmological constant, is that it remains constant in time and that it starts to dominate around 4 to 6 billion years ago.
Its influence was fairly invisible prior to that.
Well, yes.
How do we know with such precision that it's 3-point-something X more inventory than dark matter?
Right. That goes back to Einstein's field equations. And they describe the fate of the universe. So that equation that describes the past, present, future of the universe has only 3 possible solutions. And the quest in observational cosmology has been to figure out which of the solutions that we are on. And each of those solutions predicts a different expansion history for the universe. So you can go out and measure the expansion history, which is what the 2 teams that were looking at distant supernovae managed to do in 1998 and discover the accelerating expansion. And so we knew which solution we were on, and that corresponded to one in which the cosmological constant was 70-something%.
So that's how we pinned it down. It was one of 3 solutions until this very interesting supernova project that you documented very nicely in your book. One of the many things we just don't have time to go into.
Yeah.
But a really, really fascinating project.
What was lovely intellectually about this project was it was a continuing legacy in astronomy. So Hubble discovered the expansion of the universe, and he thought it was an expansion at a constant rate. He was limited by the telescopes he had. And so he could go only so far out. Until then, it looks like the universe is expanding at a constant rate. But you need to go much farther out
To see the signs of the acceleration. Yeah.
And that's what these guys were able to do because they looked and found these objects that they could detect to much greater distances. There's a brighter supernovae. So it turns out that the distance out to which Hubble had measured the expansion, those three solutions actually look very close. They sit on top of each other. So
wow.
You really have to go further back in time to start to see the divergence of the three solutions.
I'd love to briefly discuss something that we talked about in our very first conversation some months ago, the historic interplay in your field over the centuries between observation and theory.
Ideas and instruments.
Between ideas and instruments. Yeah, let's talk about that and how it led to something that almost verged on a division of labor between Brahe and Kepler, or between, more recently, Hubble and Einstein.
I've been really fascinated by this interplay between ideas and instruments and how they have interacted, not just in opening up brand new directions, but also producing methodologies and ways of gathering evidence and the ways in which to tap your imagination. We obviously are dictated by the foundational physics and mathematics that describe phenomena, but it involves leaps of imagination always because of the kinds of scales we deal with, right? They are really out of the realm of common familiarity. So we've had a revolution in the last century, starting from Hubble's discovery of the expansion of the universe to the concept of dark matter, black holes, dark energy, what have you. For each of these major conceptual breakthroughs, it has always been catalyzed by some interplay of a crazy speculative mathematical idea. In the case of black holes, they started life out as a mathematical solution to Einstein's equations. Nobody thought they would correspond to real objects. In fact, Einstein did not even like the solution, let alone that they might correspond to real objects, the end states of stars. So they started life out as an idea, and then instruments were developed, like X-ray detectors were developed in order to detect the motion of gas falling into black holes. Whereas the expansion of the universe, when Hubble detected it, there was no theoretical understanding that the universe ought to be expanding. In fact, the fact that the universe was steady was a sacred idea.
The steady state.
Not just a steady state, but the universe was fixed. It was not moving.
And what year or decade is this?
We're talking early 1900s.
And that's almost a sociological statement, a post-Victorian era, but still, but not very far post-Victorian.
This is after the discovery of astrophotography, where you could take images of the sky. So this was 1912, 1915. It's hard to imagine that at that time, we didn't even know other galaxies existed.
Right.
That's when Hubble was able to show, with the methods developed by Henrietta Swan Leavitt, with these Cepheids, they were able to measure distances and show that there were these fuzzy things you saw in the night sky were actually outside our galaxy, right? There was no theory guiding him. There were no ideas guiding him, no speculation, nothing. In fact, the universe was steady, right? That was fixed. The stars were fixed, and it was totally disorienting to think that the universe was expanding.
Also the enormity. I mean, it just suddenly went from
open up. Exactly.
All galaxies seem to be the universe, and that's plenty big.
Right.
When you look up there to realize, whoa, this is one of lots of these things. Right. So it just keeps getting bigger and bigger.
Right. So 1600 to 1900s, right? Our cosmic view spread from the solar system out to our galaxy.
Right.
Then 1915 onwards, other galaxies, and then that's it. The floodgates open.
Yeah.
And the majesty of the cosmos just gets opened up. But so, coming back to Hubble, it was the instrument, it was the telescope. He made these measurements, and those incredibly puzzling measurements, the vast speeds that were implied for galaxies that were further away from us, that they were receding, hurtling away, that just opened up. So with dark energy, once again, it was the development of highly sensitive CCDs and large format CCDs that would allow you to image swaths of the sky every night periodically so that you could catch a supernova in action when it would go off.
CCDs being digital
charge-coupled devices, that digital imaging device.
Yeah, basically you have one in your
cell phone now.
Yeah, your cell phone now.
Right. Historically, we've always had this nexus between ideas, speculation, imagination, and technology, instruments. Right?
Yep.
And computation. Computation has been transformative as well in terms of not just the capture of the amount of data, but also the kinds of analysis that we could do with data, the kind of image processing that we can do to ferret out the physics has just been tremendous. For me, what is fascinating is that we really have a grand convergence right now in terms of our theoretical understanding and our foundational physics, mathematics, and formalisms and the languages that we've developed to understand the cosmos, the computational capacity, and the sophistication of our instruments. I think they have grandly converged in the last 20 years, which is why you're seeing a new discovery in astronomy. Every day, there's something spectacular that we're finding out. And this kind of confluence has not happened before.
Because something was always bottlenecking us.
That's right.
And now at least things are in sync enough that there's no obvious bottleneck.
Now I think we're coming back full circle. And I think where the bottleneck might be is in our capacity to imagine future pathways for research, new ways to think about the interiors of black holes, for example, right? New ways to think about the multiverse and observational signature. But human beings are just so incredibly imaginative beings. And so we need people like you. We need people who are writing science fiction, who will push younger people to think beyond and come up with ideas, because the idea of direct collapse of black holes is in the realm of speculation.
Sure.
We have a lot of support and evidence from computation and so on. But till James Webb Space Telescope finds them, they're just a speculative idea, right? So I think there's a lot of room for starting with something speculative, imaginative, and trying to figure out how to make it testable. That's exciting about science in general, really.
What has it been like to be a woman in this field? Is the ratio as overwhelming as it is in high tech? Is it more overwhelming? It's funny. I happen to know quite a number of women who are involved in astrophysics. And so I feel like it may be a STEM field that doesn't have the same gender imbalance. What is it really like, though?
It depends on the subfield. So astronomical observations, there are many more women. It's not quite 50-50, but the younger cohorts are getting to be like 50-50.
Wow.
Look at undergraduates and graduate students in most programs. It's 50-50. But theory is a slightly different situation. It's not as good. So if you look at the fraction of women theorists across cosmology, stellar astrophysics, and so on, it's still probably 20%.
And that's your end of the business.
My particular end of the business, which is cosmology, this early universe stuff, it's even worse. And that's probably because it's considered somewhat fundamental. It attracts a particular kind of personality, and the culture is very particular. It's a little more aggressive than it needs to be. I was fortunate because of my career path being somewhat unusual and things having worked out the way they did. But the enduring two challenges coming through, one was the feeling of being an outsider because of the demographics and the culture of the group, right? You always feel a little bit like an outsider, and you really want to be an insider. When you're young, you want to belong. But I had actually had very good practice being an outsider in many ways, right? I'd come as an Indian student to the US.
At a time when that was much less common than it is now.
Much less common than it is now. And then also, being one of the few women who did it and went to Cambridge and all of that. But the other enduring challenge was not to change who I am and to become more aggressive or to capitulate to a very particular definition of success, and to develop the strength and the courage and the conviction to define my own idea of success. So, for example, if you are a serious scientist, it's not clear that you should be writing
popularly accessible books, as you have done.
Or articles.
Because you've written for Scientific American.
And I write for the New York Review of Books.
Right, yeah.
And I decided that I do have something very special to offer in terms of this ability to be inside and outside. And that for me, doing science is bigger than just writing my papers. It's being part of a huge intellectual enterprise that is driven by curiosity that I love. That's my life. And therefore, I need many ways of self-expression.
And you do your field an immense service, you and others like you, by making it accessible to those of us on the outside.
Especially, I think, astronomy and astrophysics, been very lucky because of how we capture popular imagination. Like, everybody's fascinated with our subject.
And you've had some great communicators with Neil deGrasse Tyson and Carl Sagan and so forth, and Jill Tarter and Brian Greene. Yeah.
So I think there's a long tradition of people doing this. What has changed, though, is that now if you talk to the public directly through your writing, that it doesn't take away from your chops as a scientist, right? What I'm doing, I feel, is something that is a little bit beyond just popularizing and simplifying the content, because I try to demystify the process of science, not just explain the results.
And again, you do your field an immense service by being one of those ambassadors to the outside world, because that's what powers the field. I mean, it was people like that who brought you into the field. It's people like that who bring everybody into any given field, scientific or non-scientific. Part of it is that outreach into the broader community. And there is also this great energy that the broader field of astronomy can tap into that I don't think any other science can. Most kids, I would imagine, developed countries have at least one visit to a planetarium, right? What is the equivalent of a planetarium for chemistry? I don't think we've got one, right?
And that's the thing. You don't even need a planetarium, right? If you live in the city and you look up at the night sky.
Yeah.
So that's what is wonderful about the subject, right?
Yeah.
The gateway is open and kids really are fascinated. And I would love for it if the kids who are really curious, we manage to keep some of them curious enough to pursue this as a profession. I understand that funding basic sciences is really fraught, but fields like ours produce these dividends way down on long time scales. One cannot afford to be sort of short-sighted about it, right? Like this example, the NSF Libraries Project, Digital Libraries Project, funded Google. The early version of Google was funded by NSF under their Digital Libraries Project. And who knew? I mean, of course, the timescale was short for them to have spun out this idea. And I think that it's really, really hard to predict what starts out as basic science and how applied it eventually gets. In astronomy and astrophysics, we've just not been as good in making those connections for the public, which is why we are still scrambling for funding.
Yeah. But still, it does say a positive thing about humanity that a fair number of immense instruments do get funded over the generations. I mean, things like James Webb is going to go up.
Absolutely.
And there are these very, very ambitious telescopes that are likely to come online in the coming decade.
Oh, yeah, there are going to be 2 30-meter class telescopes. It's a huge challenge.
And they have a very creative name, don't they?
Well, one of them is called,
the extremely large telescope.
Yeah, I was going to say.
Well, thank you so much for hosting me here in your living room, for taking so much time to demystify this magnificent realm that you inhabit intellectually most of the time to those of us who are on the outside. I appreciate it a ton.
Oh, thank you so much. This was super fun.
And hopefully to be continued.
Yeah, thank you.
If you found that conversation a tenth as fascinating as I did, listening to it will have been time well spent for you, although I guess patrons will need to have found it a bit more fascinating, maybe at least an eighth as much as me, given the length of the extended interview. Anyway, I have loved astronomy and astrophysics since I was a small child, so it's surprising that I've had so few people from that domain on this show. Really, the only other one until today was Stephen Webb, way back on episode 8 last year. He and I talked about Fermi's paradox, or the question of why we haven't seen any signs of intelligent alien life out in the universe, which turns out to be very surprising if you look at the question through a certain scientific lens. And this paradox, first enunciated by the great physicist Enrico Fermi, has countless layers of surprising nuance to it. I could talk about it for hours at the drop of a hat. Stephen and I did just that in episode 8, and I really recommend you give it a listen if you enjoyed this conversation with Priya. Now, luckily, the astrophysicist drought is over, because 2 episodes from now, that'll be mid-October, we'll have Priya's advisor from her days at Trinity College at Cambridge University in England. That's where she studied between MIT and Yale. As patrons will know, although I don't think that part of the conversation ended up in the shorter main feed version of the podcast. This advisor and friend of hers, Sir Martin Rees, has one of the coolest titles in the world, which is Astronomer Royal. He's had that post in Great Britain since 1995, and over the years he's been asked by certain dignitaries in great earnest if he writes the Queen's horoscope. He always graciously responds, well, if she ever needs it, I'm the one she'd turn to. 15 years ago, Martin wrote a book which radically influenced my view on technology and humanity's future. It has the cheery title, Our Final Hour in the US, and the more appropriate title, Our Final Century in the UK. The British title's more appropriate because in the book, Martin, writing in 2003, argued that we have maybe a 50% chance of destroying ourselves in the 21st century by mishandling some of the powerful technologies we were just starting to unlock back then. Patrons will know how much that book affected me because I talked about it in my Extra for Patrons bonus episode back in August, and the rest of you will hear more about that book when I interview Martin. But for now, I'll briefly note that he has a new book coming out in just a few weeks called On the Future. I was lucky enough to receive a pre-release copy of it, and it's a magnificent update, extension of, and expansion on the arguments he made 15 years ago. Some of you may recall that I posted a recording of myself reading a long essay to my Patreon feed back on June 30th. That essay is about existential risk, the things that could go catastrophically wrong and destroy us all. And so much of the original thinking that I presented in that essay traces its roots back to Martin's writing. I have violently rewritten that essay since June, as I mentioned last time, and I've also expanded it a lot, which is saying something because the recording of its first draft was already 37 minutes long. But it's going to be published in relatively brief installments over consecutive weeks in October, either 3 or 4 installments. We're still figuring it out. As I said last time, the publication is one you all know, and I'll probably announce that publication in my next podcast episode. And this interview with Martin will complement the essay very nicely. I'll post it roughly midway through the essay's publication run. Incidentally, if you'd like to keep up with my writing, I encourage you to head on over to my website, which is after-on.com, and subscribe to my newsletter. There's a link to do this in the upper right corner of the front page. And I promise I will not bury you in spam. I have sent out precisely 2 emails to that list since last November. I only do it when there's something significant to announce, and there will be a few such things this fall. So that's a good way to stay tuned. And it occurs to me that most of you have probably never visited my site, since almost all of you listen to this through a podcast player. If you're interested in learning a bit more about me or the 4 books that I've written, there's lots of information up there. The About Me page is a fairly personal essay of sorts about my background. And if you read what I wrote about my first book, Year 1, on the website, not to be confused with my third book, Year 0, you'll learn a bit more about my background. The other thing I like about the site is that my full archive of my episodes is laid out very nicely on the front page with pictures of each of my guests. Each episode also has a page with show notes and a short essay that describes it. So if you're interested in browsing my archive to see what you might want to hear next, the front page of my site is probably the best place to do that. Anyway, we've now come to the part of the episode in which I ask you to please spread the word about this show. The highly retweetable tweet describing my current episode is my Twitter feed as you hear this. I'm Rob_Reed on Twitter. And I may have remembered to post it to my Facebook page as well. I really need to get better about that. I'm getting close to having a large enough audience to do advertising in a quality way. And if I can get there, it will do a lot to sustain the show into 2019 and beyond. So please do spread the word. And probably the most powerful way to do this is to just tell a very well-chosen friend or 2 or 3. Because this show is quirky. It's dense with information and complex ideas. It has immense respect for the listener's intellect. And about 95% of the people out there would probably rather spend their time listening to something that's a bit less work. But if you're a regular listener, I'll bet there's at least one person you're close to who you really like to talk about ideas with. So think of who that person is. Most of us have at least one, some of us have several, and tell them about the show. I'd really appreciate it. And if your friend's mind works like yours, they'll probably appreciate it as well. And last, I'd be remiss if I didn't urge you to all please rate this show in iTunes or Apple's Podcasts app. And if you have a bit more time, maybe even write a little review of it. As I record this, there are 885 ratings up there. We're getting so close to 1,000. I'm not urging you to review the show because 1,000 is a very round and arbitrary number, although of course it is both of those things, but because this is another way to help people hear about the show. Apple's ingenious but mysterious promotional algorithms pay very close attention to ratings, and that's why it would help. Oh, and one final minor bit of housekeeping. A while back, I said there'd be 2 shows in both September and October, but because of the way the days and dates line up in the calendar, there'll instead be just 1 episode in September, this one, but 3 episodes in October, with the first one posting on Monday, October 1st, followed by the Martin Rees episode mid-month, followed by a 3rd episode during Halloween week. That's it for now. I hope you enjoyed whatever version of the Priya conversation you heard, and thank you for listening.